Okay, let's solve the quiz. And once again, I hope you realize that you need to learn how to solve these oscillation questions to be practically there are three topics in the final, right? Oscillations, angular momentum, and rotational dynamics, part of rotational dynamics. So I think it's a good idea to learn to solve these basic questions. So let's first understand the geometry. Geometry here is, I'm looking from the top onto a frictionless table. There is a rod, uniform rod of length L and mass m that's fixed from one point. So this is the pivot. And it's attached to a wall, if you want, a stable part, by two springs, as shown. Both springs have spring constant k. What does the question ask? Find the angular frequency of small oscillations. Okay. So how do I solve these problems? Not very hard. What I should actually think is that what happens if this rod makes an angle theta with the x-axis. Now I have both springs are stretched, right? So both of them will apply a force on my rod, which means they apply a torque. That torque is trying to restore my rod to the equilibrium point. So what I need to do is I need to calculate the torque due to both of these springs. So let's try to calculate F1 and F2 first. How do I do that? Well, how much is the first spring stretched? The length here is L over 2. So that stretching of the first spring is L over 2 times sine theta. How about the second spring? 2 times that, right? The full length is L, so this is going to be L sine theta. So the torque due to first force, F1. What's that? It was R cross F. R is L over 2. F1 is F1. Okay. How about the angle between them?
It's almost zero.
Well, okay. It's almost zero. I mean, if I need the sine of that angle, right? That's equal to, approximately equal to cosine of the, let's see. So F1. So it's actually going to be cosine theta. Okay, that's the force. That's because the angle between F1 and R is 90 plus theta. Okay, then you can actually write it's 90 plus theta. This is 90 degrees. That's theta. It's cosine theta. And how about F1? F1 we said is L over 2 sine theta. So torque 1 is L over 2. F1 magnitude is K times L over 2 sine theta. And now I have cosine theta. Yes?
But spring also shifts by some angle, I think.
That's a very good question. So that's actually right. I was trying to, be quick and fool all of you, but you were not fooled. So here is the thing. If I have a rod, and let me just do it for one spring. And if this length is L, that length is, let's say, capital L. When I turn this guy by a large angle theta, the spring will also start to make another angle here. right? And it's not going to be easy to calculate how much the spring has actually extended, right? Also, the direction of the force here is not easy to calculate. However, we know the following. For large angle, if I actually calculate, let's say, the new length of the spring, I need to do it looking at the following triangle, right? The original position. Let's do it in blue. Here is another triangle. So this length is L, right? This length is capital L. I must make sure that new L prime and L are related. And how are they related? I need to find the full angle alpha here. And the length here is square root of L square plus L square. Hey, you don't come into my lectures late. Please go out. It's amazing. This is the last, just one lecture before the end of the term. So it's quite remarkable. Now, so what is L prime square is going to be L square plus small l square plus capital L square minus 2L cosine alpha, right? Now, no, alpha is the full thing here. Okay. So here's the problem. Go ahead and do that calculation. Okay. What you will see is when theta is much smaller than 1, you will find out that because sine theta is theta, but also tangent theta is theta, you can equate approximately tangent theta to sine theta. That's why, because of that equivalence actually, okay, I don't have to do this calculation. Don't need this. Essentially, when you're looking at small oscillations, always assume that everything moves on a circle. So you don't need to calculate that small rotation. Okay?
Ask a question.
Sure.
In the quiz, I approximate that angle by approximately 90. For that reason, I didn't take that into account cosine theta.
Let's see what this gives me. Okay? If what I'm telling is correct, then your result also should be correct. Okay? Now, here's the thing. This is tau 1. But which way is that torque trying to rotate my rod? Clockwise or counterclockwise? It's trying to rotate clockwise. How about tau 2? I don't have to write it. It's just instead of L over 2, I'll write L. So it's going to be L square K sine theta cosine theta. Again, trying to rotate it clockwise. So the full torque is 1 over 4 plus 1 is 5 over 4 L square K sine theta cosine theta. Okay? Now I've calculated the torque. What do I need? I also need the moment of inertia. I'm amazed that no one actually asked me what the moment of inertia of this rod is, presumably because everyone remembers. Really? I'm amazed. So now I would say the moment of inertia around the pivot point is 1/3 ml square. So what's my equation? My equation is simple. Torque is equal to I times alpha. So torque I have calculated 5/4 L square K sine theta cosine theta is 1/3 m L square d square theta dt square. But the way I define theta, theta is counterclockwise and the torques are clockwise. So I must have a minus sign here. Here's the thing. Is that a differential equation I can solve? Okay, this is not a differential equation you can solve. I can solve it, but that's a joke. Come on, man. Come on. So this is the last week of your first term at Bilkent. You should be more happy, right? Okay. So I cannot solve this. You cannot solve this. We need approximations. And we've already done approximations. We've said theta is small. So what is when theta is much less than 1? What did we say sine theta was? Sine theta was approximately theta. How about cosine theta? Now, do you remember what cosine looks like around 0 theta? It has a maximum, right? So if I'm going to fit it with a line, what the logic was fitting everything with a line, right? So that line would actually be flat. Its derivative is 0. So I just need the value at 0. Cosine theta for small theta is exactly 1. Okay? So approximately I have 5/4 k theta is minus 1/3 m d square theta dt square. And every time I see a differential equation like that, I know how to solve it. I know that I've really used my space terribly, so let me rewrite this equation somewhere else. Okay, so I'm going to write this in a better form. D square theta dt square is minus 15/4 k over m theta. And anytime I see an equation like this, I know that the solutions as a function of time are going to be sine omega t and cosine omega t. And taking two derivatives of such a function is multiplying it by minus omega square. So I can read off what omega square is. Omega is square root of 15/4 k over m. All right? Did anyone find the correct result? Well, 3 cases, not too bad. That's very good. That's very good. Now, it's good because I'm trying to stay positive, right? Okay, so now let's check. Did I reach my goal? Yes, I did reach my goal because the question asked me to find the angular frequency, and that's the angular frequency of small oscillations, right? Sorry. And how about units? Okay. What should be the unit of omega? Should be 1/2. Let's check. Square root of unit of k. What was the unit of spring constant? I remember F is equal to kx, so k must be F over x, which is newtons per meter. M is kilograms. Newtons is kilogram meter per second square divided by meter divided by kilogram It's 1 over second. So it does check. That's good. How about some limits? And here's the thing. I cannot really check any limits here. I mean, this is square root of k over m. You remember the oscillation frequency of anything that's tied to a spring with an effective mass m is going to give you square root of k over m. You,
M goes to infinity.
yes, m goes to infinity. This thing should not oscillate. I can see that is the result. But I'm not quite sure if it gives you, I mean, is there any way to check that number 15 over 4? Units cannot tell us about that coefficient. The only way you are going to get that correct is if you did the correct calculation correct. So you should not be sloppy. You should be careful in your equations when you're solving these oscillation problems. Okay? Question. Oh, well, historical reasons is I think that's the only thing I can actually say. Oh, so there was something which is in your book and I did not tell. Maybe it's going to clear up your question. So let me tell this at this point. People have calculated the following. People have looked at the following. Let's say, if I have some mass moving with velocity v on a radius r, okay, this is uniform circular motion. We know what this guy does. It goes on a circle, right? Now, here's the thing. Let's say I have a light source at the top. What happens? What do I see if I look at the shadow? What does the shadow do? The shadow is basically just the x component of this uniform circular motion. I know that here in my uniform circular motion, x of t will do the following. It's going to be, if this guy makes an angle theta at some point, well, it will be r times cosine theta of t. But what's theta of t if this is uniform circular motion? Theta of t is going to be v over r. That's going to be omega times t. So x of t is r times cosine omega t. Okay, that's why we call this omega. It's essentially the angular frequency is the angular speed of the corresponding uniform circular motion. Okay, so there is a one-to-one correspondence between uniform circular motion and simple harmonic motion. Okay, I don't know if that answers your question, but that's the. And I think it's clearly not important at this stage. When you study oscillations deeper, you'll see that the best way to treat these kind of differential equations is to treat x, our position, as a complex number. Then it becomes actually quite simple to do all of our calculations. Yes?
So in the exam, if we are asked to find the oscillation frequency,
Find, if it says oscillation frequency, find f. If it says find the angular frequency of oscillations, find omega. Okay? Let's solve one more question. Ropes and pulley massless. There is G. Find the small oscillations find the frequency of small oscillations around the equilibrium point. Yes?
The equilibrium point of this spring is not the real equilibrium point of this spring, natural.
Yes, it must be larger than the natural length. That's what we'll find out, right? We're basically saying, first find that the new equilibrium point, then let's see if it actually makes any change, all right? Does everyone understand the question? Now my pulley is tied to the ceiling, not with a string, but by a spring. So when I actually, there will be some equilibrium point, and when I give a small disturbance to this M, there should be small oscillations in the position of the mass. Okay? Good. So so how would I solve it? First of all, let's figure out what the equilibrium point is, how much the spring is stretched in equilibrium, all right? Now, if I'm in equilibrium, what are the forces on M? The forces on M are mg and the tension in that string. And if I'm in equilibrium, A is equal to 0, which means T is equal to mg. Great. Then, can you tell me what's the force let me call it F2 of the spring. Well, now I'll do the free body diagram for the pulley. It's being pulled down by 2T, and it's being pulled off by the spring, F2. So its acceleration is 0, which means F2 is 2T, which is 2mg. So can I find how much this spring is stretched? What's the stretching of the spring? Yes, I can. So call the stretching of the spring delta. I know that K times delta must be equal to 2mg, which means delta is 2mg over K. Good. Now, I need to consider a situation which is not in equilibrium, right? So I need to calculate. Let's draw this. I need to calculate what happens if I move this mass down with x. I think to be able to move that mass down by x, the pulley also has to move down, right? Why? Because the string is not stretchable. It doesn't extend. And it's tied to, although it doesn't look tight here, it's tied to the floor, right? So now the pulley has moved down. How much has it moved down if the mass has moved down by x? It must actually move down by x over 2, right? Because it has two sides. The spring actually has to stretch by x over 2 to accommodate the motion of the mass by x. Good. Then what would be the force F on the spring? F will be, well, K times the old length plus x over 2, right? That would be my. Good. So I'm just redrawing this. T and F2. I've just calculated F2 is K times delta plus x over 2. Good. How about the dynamical equation for my M? Now, let's start with the pulley. The dynamical equation, it will be pulled down by 2t and pulled up by F. Will there be an acceleration of my pulley when I'm accelerating this mass? Yes, there will be an acceleration. Okay. Probably down if M is moving down. But what's Newton's equation here? M pulley times A is 2t minus F. F2. What's M pulley? We said it's a massless pulley. M pulley is 0. So when I have a massless object, the only way it can actually move is when the forces on it are equal to each other. So T is 1/2 times F2, even in the dynamical situation. Should I go over this again? I'm writing F equals ma, but I'm saying M is equal to 0 for this pulley, which means at all times the net force on it must be 0. Okay? Good. Then how about the free body diagram for M? Here is M, here is T, and this is mg. If my x is going down, so my A must be going down. What will be my A? M times A would be mg minus T. But, okay. Now, M times A is mg minus T is 1/2 F2. And what is F2? MA is mg minus 1/2. F2 is K times delta plus x over 2. K times K times delta plus K times delta plus x over 2. Okay? Now, so m times d square x dt square is mg minus 1 over 2 k delta minus 1 over 4 k x. Okay? Now, what was delta? We have already calculated delta. Delta is 2 mg over k. if delta is 2 mg over k, k's cancel, 2's cancel. This is mg minus mg. That's already my equilibrium condition. So what do I find? I find d square x dt square is minus 1 over 4 k over m times x. And this is exactly the kind of differential equation I can solve. It tells me that omega square is k over 4m, or omega is 1/2 square root of k over m. Okay. So the nice thing is, as long as I'm looking at oscillations around the equilibrium point, where that equilibrium point is did not matter. That's actually correct. If you consider another example, let me ask you a multiple choice question. I have a no. I have these three situations. I have a mass suspending from a spring, a mass on the horizontal plane with a spring, and a mass on an inclined plane with a spring. Now, in which case is the length of the spring largest? In which case is it stretched the most? Third case. So L3, let's say L2 and L1. I know that L3 must be larger than L1, must be larger than L2, right? Why? Because there is no force in the L2 case, so it's actually natural length. And in the other two cases, there's a force pulling it down. How about omegas? How about the frequencies? Which one oscillates the fastest? It turns out all of them are the same. Okay. Why? Because I'm looking at oscillations around the equilibrium point. Okay. Please do the algebra. Please make sure that what I'm telling you is correct. Okay. So that's actually, if you have a really quadratic system, the point of equilibrium does not care where you are. Let me just mention one more problem, but really not solve it. So again, a massless pulley with small m attached to its edge. I'm going to ask two things. Find theta 0 for equilibrium. Find the frequency of small oscillations. How do you find theta 0? Let's think about that first. What should be our equilibrium condition here? In equilibrium, my pulley should not rotate, right? So the net torque on that pulley should be 0. So this is, of course, G. So what are the sources of torque here? I have mg, so that in equilibrium T is equal to mg. So there is a torque coming from the rope, but there is also another torque. Here is my small mg, and this length is r. But the torques of these two forces are in opposite senses, in opposite directions, right? So what I would say is that torque 1 is mg times r times sine theta 0, and torque 2 here is going to be capital mg times r. So small mg r sine theta 0 is capital mg times r. So it turns out sine theta 0 is over small m. Okay? Yes? That's an excellent question. What happens if the capital M is larger than small m?
Thing moves and the arm goes up and the large arm comes down with an angle. At some point, this will have more distance, so the torques will be equal.
No, it turns out that's a very good question, and we've solved it correctly. Sine theta 0 is capital M over small m. What if, let's say, capital M is 5 kilograms and small m is 1 kilogram? It means we need to find an equilibrium angle sine theta which is 5, right? No angle actually has a sine of 5, okay? So if m is larger than m, then there is simply no equilibrium. Which means if I tie these things down, m will start going down and small m will just keep rotating. There is simply no equilibrium, okay? But this is a very good observation. You should always think about what you have found, different limits, okay? We have 1 more hour to go. Let's take a 10-minute break.